Your final exam skill is the same proof procedure, or the same proof theory, at any rate, with the addition of 10 rules of inference, called the rules of replacement. We have to adopt actually a different procedure because there's simply not a linear step-by-step process by which we can complete these proofs. But we do have a handful of strategies that we can use. So I'm going to start out tonight by introducing these rules of replacement. And I'm going to present them in a format that's a little bit different than the way they're presented in the book. I suggest you copy this format and turn it into a sort of a chart that you can refer to easily. It has some advantages over the way it's presented in the book. So after we go through these rules of replacement, I'm going to look at a couple problem areas that crop up with the use of some of them. The first one we're going to look at is called association. Association has two versions, one involving dots, one involving wedges. So, involving conjunctions, association allows us to move the main punctuation around 2 of 3 conjuncts. When we're dealing with wedges, it allows us to do something similar, move the main punctuation around 2 of 3 disjuncts. So these pairs of statements right here, they mean exactly the same thing. And so we can replace them, one with the other, in our proof procedure. This can be replaced by that and vice versa. That's why I'm repeating the first one at the end. They replace each other. These pairs of disjunctions mean exactly the same thing. And so we can replace one with the other in our proof procedure. This replaces that. This replaces that. I think you should jot down a tip about what this is most commonly used for. Either by itself or with our next rule of replacement called commutation. This rule is used to alter the appearance of a conjunction or a disjunction. And the reason we would most commonly want to do that is so that we can have the kind of dot or wedge, the kind of conjunction or disjunction that we need for simplification or disjunctive syllogism. All right? Questions about association? I'll give you a moment to finish that if you have a question. Move the main punctuation around 2 of 3 conjuncts or 2 of 3 disjuncts. We're altering the appearance of our conjunction or disjunction so we can get the sort of dot or wedge we want, typically, not always, typically for simplification or disjunctive syllogism. See, we're altering their appearances to get what we want for that first premise. Okay, done with that? Questions? Next up is a rule of replacement called commutation. Commutation also has two applications, dots and wedges. So again, we're altering the appearance of a conjunction or a disjunction. Here it should be more obvious why we would want to do this for simplification or disjunctive syllogism. With simplification, we can only extract the left-hand conjunct from a dot. We can never, until now, touch that right-hand conjunct. But if we take the intermediate step of commutation, we'll have that right-hand conjunct on the left-hand side, and we can simplify it. With disjunctive syllogism, previously, we could only extract the right-hand disjunct from a wedge, right? Suppose we want the left-hand disjunct. Well, we'll take the intermediate step of commutation, get it on the right-hand side, and extract it with disjunctive syllogism. Now, these aren't the only reasons why we use these, but they're the most common. And again, very often association and commutation are used together, one at a time, of course, to dramatically alter the appearance of a conjunction or a disjunction. Good? Next up is a rule of replacement called transposition. Transposition has only one application. Basically, transposition allows us to alter the appearance of a conditional statement. Now, it looks like what we might be doing is transposing or reversing the order of the antecedent and the consequent, and we're definitely doing that in every case. But it also would appear that we're adding or removing curls from each of them. That's not always necessarily the case. This one is a little bit problematic in recognizing what counts as a candidate for transposition. So we're going to come back to that after we go through all these rules. Why would we want to alter the appearance of a horseshoe? To make it look the way we want it to for perhaps one of our first 9 rules of inference. Modus ponens, modus tollens. Very often used in hypothetical syllogism to manipulate horseshoes so that we can use them in hypothetical syllogism. Questions about yes?
In our textbook, it has it abbreviated as TRAVS.
It's a misprint. It's a typo.
Okay.
Yeah. I wonder if that's in the 14th edition. Is that the
No.
inside back cover of the book?
Oh, the 12th, at least.
It's in the 14th too? See? Nothing's true just because it's in a book.
Yeah, but it doesn't show it here. It does it right here, so.
Well, that's good. Okay, next up is a rule of replacement called exportation. Exportation has only one application. Again, exportation allows us to alter the appearance of a conditional statement. Why would we want to do that? Same reason we use transposition. To get the sort of horseshoe we want, typically, for modus ponens or modus tollens or hypothetical syllogism. That's not the limits of its use, but that's most common. Now, these first four that I just went over, I did in the order I went over them because you should also note that when you replace one of these statements with its logically equivalent statement, you're not changing the kind of compound statement you're dealing with. Commutation, if you're replacing a dot, it's still a dot, it just looks different. If you're using commutation with disjunction, you replace a wedge with a wedge, it just looks different. Same with association, transposition, and exportation. These next two probably do change the kind of statement you're dealing with, but not necessarily. But I'm going to group them together because after those two, our remaining rules of replacement definitely change the type of compound statement we're dealing with. So next up is double negation. We'll describe double negation simply as adding or removing two curls from any statement. Any statement, simple or compound, add or remove two curls.
I like two regulars with a positive.
Well, why would we do that? If a premise in an argument whose validity we're proving has two curls, most likely we're going to be removing them. Most likely. Not always, but most likely. We'd be adding them when we need that type of double negation for modus tollens or disjunctive syllogism. Yes?
Say the statement was longer, could you add it to any two parts of the statement? Or does it have to be added to?
Give me an example.
So P and Q, or P, and could you negate P and negate Q? Or do you have to only?
You have to apply two curls or remove two curls from any statement.
Single statement.
I can add two curls to that entire component.
Okay.
I think you're asking, can I do this?
Yeah.
No. No. Questions, double negation? That's pretty easy to remember. You've got that one down already. Probably commutation and association as well. I mean, that's three you don't even have to bother to memorize. Probably. And next we'll look at tautology. Tautology has two applications. How shall we describe this? Add or remove a redundant conjunct. Add or remove a redundant disjunct. Why the word redundant? Well, you'll notice that the variable p is repeated here. So, whatever statement you're replacing by tautology, okay, you want to make a dot out of it, it's got to be that statement in conjunction with itself. Those can't be different statements. Get it? Same thing with disjunction. So if I'm replacing D, some statement D, by tautology, it would have to be D wedge D. That's why it's the same variable, P. Why would we do that? We might need a wedge for a constructive dilemma. Probably you'd be removing one of these conjuncts if it exists in the argument. If this exists in the argument already, probably we'd be reducing it to P, most likely. That one's easy enough to remember. The remainder are pretty complicated. So let's see, what shall we do next? I think we'll look at De Morgan's theorem. De Morgan's theorem has two applications. Okay, the left and the right-hand side of that line, those are different statements, but I think we could describe both sides in the same manner. What we're doing with De Morgan's theorem is changing the type of compound statement we're dealing with. So for example, actually they can't both be described in the same way. I'm wrong about that. So I'll describe them separately. That was an error. Okay, we're replacing a curl with a wedge or vice versa on this side. I know there's a little bit more going on there, but that's the basic description. Replacing that curl with a wedge, or vice versa, that wedge with that curl. On the other side, replacing a curl with a dot, or vice versa. So this is dramatically not only altering the appearance of our statement, it's actually changing the kind of compound statement we have. But they mean exactly the same thing. These are logically equivalent statements. Well, why would we want to replace them? We have a wedge and we need a curl for disjunctive syllogism or modus tollens. If we have a curl that looks like that and we need a wedge for a constructive dilemma, we're swapping out symbols, swapping out compound statements. Questions about De Morgan's theorem? No. I think we'll look at material implication next. Well, we're replacing a horseshoe with a wedge, or vice versa. Replacing a horseshoe with a wedge. If we have one and we need the other for any of our first 9 rules, that's why we would do it. I think we have just 2 more, distribution and material equivalence. That should be 10, unless I'm forgetting one. Questions about material implication? Distribution is probably the most complicated rule of replacement. It's got 2 applications. Well, both sides of these can be described the same way. In any case, we're replacing a dot with a wedge or vice versa. But you'll notice the dots on either side are quite different statements, as are the wedges. But in any case, we're replacing a wedge with a dot or vice versa. You'll notice this left-hand conjunct is distributed, therefore the name, to these disjuncts. And this left-hand disjunct is distributed to those conjuncts. You know about our rules for substitution. It's got to have that form to qualify for distribution. Questions about that one? That should be 9 of them. Why don't somebody verify that for me?
Yeah.
All right, there's just one more. It's called material equivalence. It's got 2 applications. Both involve the tribar. So on this side, we're swapping or trading tribar for a dot, vice versa. On that side, we're trading or replacing a tribar and a wedge, or vice versa. tell you something about material equivalence. You'll notice that none of our first 9 rules of inference, modus ponens, modus tollens, all that stuff, none of them specifically use a tribar, right? There could be one in there, but the rules themselves don't involve tribars. So if the argument whose validity we're proving has a tribar in it, I can tell you that most likely we're going to replace that tribar with the dot or the wedge because you could do so much more with them. Okay? Simplification, disjunctive syllogism, etc. All right, those are our 10 rules of inference. Now I want to go over a few of them that present problems for our identifying what counts as them. There is a slight problem with material equivalence, although it's not that one. It's not a problem with identifying what counts. It's a matter of exactly what can I do with it. So let's clear that up. It would probably never occur to you to do what I'm going to tell you you can't do. But just in case it does, we'll get it straightened up. Okay, we're saying that this conjunction means exactly the same thing as that tribar. Not all conjunctions, all tribar, looking like that, right? And we're saying that this wedge means exactly the same thing as that same tribar. So let me ask you this. Would you say this conjunction means the same thing as that disjunction? This is materially equivalent. It means exactly the same thing as that statement. And this means exactly the same thing as that statement. So, do you think that they mean the same thing?
Yeah.
Yes, they do. They do. But here's what I need to point out to you. You can't replace this with that in a proof, at least not immediately. You have to take the intermediate step of turning one of them into the tribar. Right? You can remember that, right?
So this is
If I have a statement of this form and I want that, I can't just replace this with that. I have to take the intermediate step of turning this into the tribar and then replace it. Yes?
so it'd just be 2 steps of a proof rather than the
If I wanted to get from here to here, that would be a 2-step procedure. Yep. Okay, let's see if I can remember all the little problematic ID problems, identification problems. There's one involving association. And there are so many examples of this that I could go through that are much more complicated than what I'm going to show you. It's really not worth it. I'm just going to give you an example of what might be difficult to recognize as an example of association, or what can you do with it. And then if some more complicated example comes up in our proof, I'll point it out. Let's just take the dot as an example. Okay, those are our logically equivalent statements by association. And a spot-on substitution of either one of them presents absolutely no problem. Everybody should be able to recognize that as a candidate for replacement by association. If not like right this moment, then next week or the following week after we use these. And so if I were to replace that, well, that's its replacement statement by association, right? No problem. But let's remember, whatever is replacing a variable can itself be complex or compound. See? And when that's the case, it's not always easy to see what counts as replaceable. So I'm just going to give you one example. Now, most people the first time around would not recognize that as subject to replacement by association, but it is. Can I substitute A dot B for P? Yeah. Can I substitute C for Q? D for R? So does this count as a statement replaceable by association?
Yeah.
Okay, I'd like you to jot down, if you can, what would it look like if I replaced it? Got it? Read it off for me.
Okay, it will be bracket,
Yes, sir.
parentheses, A and B, parentheses, and C, bracket.
Is that it?
Oh, and D.
Okay, that's it. So why don't you just record that for your notes? And I think you could imagine that there are much more complex examples than that, because each of these variables can be, very compound and punctuated. I don't think we're going to encounter anything more problematic than that. Let's see. Commutation, no problem. Association, that little quirk. Let's see. We looked up. Transposition poses some difficulties. So let's have another look at that. That's our transposition. This poses problems for recognizing or identifying what counts as a substitution instance of either one of those statements. Because I'll grant you that any horseshoe whatsoever can be considered a substitution instance of this statement form, but not that one. So let's look at some examples. Starting off with the obvious. Is that a substitution instance of that statement form right there?
Yeah.
Sure it is. So if I were to replace it by transposition, what would it look like?
Not A, horseshoe.
Not
Yeah.
Oh, I think that. What do you think?
Yeah.
Okay. Am I blocking you? That's because I'm right-handed. Well, keep it easy for now. Is that a substitution instance of this?
Yeah.
Now, if I consider this a substitution instance of this statement form and replace it with this, what's that going to look like?
Not A, horseshoe, not B.
Thank you. We're considering it as a substitution instance of this. So we're transposing these two and adding a curl to each one. Right? Is that a substitution instance of this? We already know we can consider it as a substitution instance of this. We just did that. Curl, curl A, horseshoe, curl, curl B. But can't we consider it a substitution instance of this? Okay, so I want you to either conceive or jot down, if you have to, what would the replacement statement look like if that's a substitution of this statement form? What would we achieve?
Not B.
No. What?
A, horseshoe, B.
Yep. You verify that? You really should, I hope you're noting this somehow, because these things occur frequently, and the books never, they expect you to recognize it, like right off the bat. And I couldn't, so I don't know if you can. That's great if you can. Okay, one more. Can I consider that a substitution instance of this statement form? No. Because both antecedent and consequent would have to be negated, and they're not. So that could only be considered a substitution of this statement form, correct? And our replacement statement would be that. If you want to get rid of those two curls, you have to take the additional step of double negation. Yep.
I kind of know the answer to this, but I think this confused me really bad before. But if it was
Before what? I mean tonight sometime?
no, like last
Oh, okay.
couple weeks.
You actually
But
read ahead?
If it was curl parentheses A horseshoe B.
Hold it.